Alright, so this is the final question on the 4c&d FIP quiz. This is the solution for number 6. This is cardboard sledding on the big hill in Rogers. You're not given any mass, but you are given the coefficient of friction, and you're being asked about the magnitude of acceleration. So let's start off by doing, realizing that we have 3 possible equations to work with. And since the acceleration is all going to be on the x-axis, it's probably a safe bet to assume that we'll end up substituting into that. So we'll start with mu k equals fk over fn, and we're not sure what we'll need that for yet, but we know we'll probably need it. And then we have a sum of forces on the y, which is 0, and that's fg plus fn. So we know that fn equals negative fg, or vice versa. Actually, let's negative fg equals fn. So fn equals the negative of mass, fg on the y. That's really important. Because of course our gravity here is split onto a force of gravity on the y and a force of gravity on the x. So this is mg cosine of theta. So we have an expression for fn now. That means it's a fair bet that we'll have to use the mu k equation to get an expression for fk. So let's go ahead and do that as sort of a safe bet. Mu k fn equals fk. Okay, so we've now got 2 expressions built. I'm going to circle those in red that are probably going to be pretty useful, and I'm going to shrink all of that. So now we're ready to start looking at our x-axis where our acceleration is going to happen. So we know that whatever the sum of forces on the x is, the net force on the x, is going to be equal to mass times acceleration. And it's also going to be equal to this force of gravity x, f of gx, plus the force of kinetic friction. Now I'm going to do something that's, I won't say revolutionary or controversial, but because on a standard Cartesian coordinate system, this would be the positive direction and that would be the negative direction, I'm going to go ahead and assign this f of gx a positive. So I'm going to note that this has to be a positive number, this overall has to be a negative number. And in doing that, I'm using the convention that, basically the force that's opposing the motion is negative. And that's another convention we very often use. So it's, a little bit dicey, but we're going to go ahead and, so we'll just, for this g, we'll only use the magnitude of acceleration due to gravity. We'll use negative 9.81. We'll just use 9.1. Okay, so let's go ahead and do one thing first. One thing that saves a lot of hassle here is if you can, in a problem like this, you actually are able to do a lot of your rearrangement before you start substituting in, and that avoids you having to move a lot of things across the equal sign and change signs, and that simplifies life. So if we divide this side by mass, we now have, in essence, our solution. Now we just need to substitute in for our f of gx and our fk. So let's go ahead and rewrite this. So acceleration, well, f of gx is equal to mass, gravity, times the sine of theta. And fk, if we go up here, is equal to mu k times fn. And this whole thing, of course, is divided by mass. Well, we're not out of the woods yet because we don't have fn, but we have an expression for fn. So I'm going to move and shrink some things, and then we'll plug that in. Okay, so I've rewritten the expression, and now I'm just going to put in the expression we built for fn, and that's negative mg cosine theta. And in most cases, we would be saying that this is a negative number, so we want to make sure that if we're remembering that this one was positive and this one was negative. The big thing we want to remember is that this number is being subtracted from that number. So we just want to get the magnitudes of both of them and then sort of do our operations as necessary. Okay, I'll get rid of that now. So we're ready to do a couple things. Number one, remember that you weren't given mass here, and initially that looks like it's a problem, but you realize now you can just cross out the mass, and you could actually factor out a g here if you wanted to. You don't have to, but it does simplify the algebra a little bit. So I'll go ahead and shrink some stuff, and we'll do our final step. Okay, so I've rewritten the expression, and I've put these little brackets in here just to remind myself, and I'll redraw those in a different color, that this number has to be a positive, and we have to, in essence, subtract the magnitude of this number from it. So let's go ahead and plug some, well, we'll factor out the g first. So we get acceleration equals g times quantity sine theta, and that has to be a positive, plus this whole thing, mu k, negative cosine theta, but whatever the magnitude of this is, we're going to go ahead and make it a negative. So I'll shrink and rearrange and plug in numbers. Okay, so we've got everything plugged in here, and I've done the thing that the book does, where I've just used the magnitude of acceleration due to gravity, and I've left the signs sort of to their own devices. And here, we've maintained that negative sign on this portion, so it ends up as a negative. So when we do our final arithmetic, we end up with a raw answer for acceleration of 1.042558608 meters per second squared, and with sig figs that gives us an acceleration of 1.04 meters per second squared. Okay, that's the last one. Hope these are helpful, and see you tomorrow.